Today we're going to talk about momentum and impulse. And yesterday we learned what momentum is. It's the product of the mass times the velocity. P equals mv, right? And the dude in the video there was explaining all the different stuff about vehicles. In fact, he was explaining a lot of things that I haven't come to yet. So it was sort of a good preview, I guess, of the whole year. So we are going to derive the impulse momentum equation from Newton's second law, the simplest derivation in the history of deriving, relate the impulse momentum equation in real-life situations, and solve problems using the impulse momentum equation. And the reason that there is a golf club and golf ball is because that is a real-life situation where the impulse momentum equation is applicable. What's that, Tyler?
I just wrote the date in December 15th.
Oh. Oh, I sometimes start my check with 19 on them still, so it's been a few years since it was 19.
Oh my god! That's pretty bad.
Yeah. Exactly. Anyways, thank you, EJ. Anyways, thank you for not judging me.
You can see
The nature of momentum. Now, this is just sort of introductory, sort of setting the tone, right? You don't need to write this down. Just sit back and enjoy. Right? So, consider the following examples. Car and a train are traveling at the same speed. So imagine Ty is racing to beat the train at the crossing. Bad idea. Bad idea. They're traveling at the same speed. It would require more force to stop the train than the car. Why is that? Train is huge, like many, many, many times more massive. And in other words, it would have more momentum. Another example, a bullet fired from a gun penetrates a wood block more than a bullet of identical mass thrown by hand. So like you either shoot a bullet into a wooden post or you throw a bullet. Well, the one that you throw is just going to bounce off, right? Unless you've got cannons. Exactly. Okay, so those are sort of ideas about momentum. So again, these two cases are a result of momentum. And this is kind of a mathematical review of yesterday, I guess. Momentum is the product of the mass of a moving body and its velocity. So that's the formula that I showed you yesterday. P equals mv, and in fact, the P and the V are both vectors. Now, think way back to grade 11. You might remember this old gem. A equals delta V over delta T. Remember that? Okay. Change in velocity divided by change in time. Okay. And Newton's second law, you might remember from mid-grade 11, F equals ma. Remember that, Josh? Okay. So is this A and that A equal to each other?
Yeah.
They are indeed. Right? So we're going to get F equals M. Instead of A, we're going to go M delta V over delta T. Right? All I've done is plug that delta V over delta T in there. Right? Okay. Now, generally, we like to rearrange that. Okay? So we could write this as, and I'm not 100% sure what's on the next screen, but I'm going to write this as M delta V over delta T. I guess there should be a delta there. M delta T over delta, please.
Oh my goodness.
Let's just start that all over again. Let's go back into 1990. I was telling the student this morning that there was, I don't know what we were talking about, but I was okay, so M delta V over delta T. We're going to rearrange that into this common equation that you should write down. That's the one you need to know. That's the derivation. That's it. Nice, eh? Easy, simple. M delta T equals F delta T is equal to M delta V. F delta T is equal to M delta V. Now, I like to think of the deltas, if you think of them as capital A's. Right? See how it's kind of like an A? Fat equals MAV. I call it the fat MAV equation, which is way easier to say than the impulse momentum equation. Right? So it's a fat MAV problem.
That'll help me memorize it for university, right?
Yep. You'll forever know it as the fat MAV. The deltas?
In there when we're writing it down.
You should. Because quite often in these situations, Danielle, the velocity is not going to, the starting velocity is not going to be 0. Okay, so it's probably a good idea. As a reminder, yes. Good question. So the product of a force and the time interval during which it acts is called the impulse. So the fat part, the left-hand side, is known as the impulse. Force multiplied by time is known as the impulse. And it doesn't say it on here, but there's a special letter for impulse. We use the letter J to represent impulse because it's the next letter after I for impulse. I don't know. They don't use I because I is for current because, you know, yeah, I don't know why. I don't know. It gets a little crazy. J is for impulse. So the fat part is called the impulse, the force multiplied by the time. And it can also be referred to as, because this is m delta v, well, delta v and m times v is what? Momentum. So with the delta in there, that's the change in momentum. So delta p, the change in momentum, is the mass times the change in velocity. Does that make sense? Change in momentum.
Is that a formula for you?
You might, yeah. Yeah. So when you apply a force over a period of time, you change the momentum, right? So if you think about Angry Pac-Man right now, what is, I will assume gender is male, but it's probably a non-gendered foam ball. What is the momentum of Pac-Man right now? 0. I apply a force, and he has a change in momentum, right? Change in velocity. Okay, now, what if when I hit him, what if instead of, I need a smaller one here, it's too big. I need like a small wooden ruler. Yeah, I need like a wooden ruler.
Got one right here.
Do you? Is it a wooden one? Perfect. Can I borrow it? Hopefully I don't get Pac-Man blood on it. If I don't follow through, how far does it go? It won't go anywhere? Like you know what I mean? Does everyone know what I mean by follow through?
Yeah.
Okay, right? So if I just go like this and then stop, right? Doesn't go very far. But if I follow through, time's already deep ahead. If I apply the same amount of force but follow through, heads up, Karen and Josh, and maybe someone over there, I'm not really sure where this is going. If I follow through, it goes a lot farther and goes a lot faster, right? Because as I pointed out, I'm increasing the, I'm going to hang on to it, because I might need it. I'm increasing the time. Okay, and that is the whole idea of this. You're increasing the time. Since the change in momentum depends on the force and the time that the force acts, this has some use in sports. Following through. When you swing a baseball, when you first learn how to play baseball, the coach always tells you to follow through. A lot of coaches don't know why. It's because following through will increase the time. So you've applied that force over a longer time, so you're increasing which side of the equation? So left, if I go F delta T is equal to M delta V, well, if the force remains the same, if I increase the time on the left-hand side, the only way to make the equation, right? An equation means the same on both sides, give and take, like a negotiation. Can the mass of the Pac-Man change? No. So the only way to make the right-hand side equal is to increase it. And when the velocity increases, then it goes further. So that's why you follow through. And it doesn't matter whether it's baseball, or hockey, or golf, volleyball, anytime you are basically hitting or throwing a ball, you want to follow through. Okay? Now, it also has this application. I used to have a really short little copper tube that I used. And it didn't really work. It worked really good, but it's not missing. I really wish I could find it, because it was really cool. So I prepared this little marker thingy here, and I'm going to put it in my mouth, and I'm going to blow it, see how far I can get it to go.
Oh my God.
And I'm going to fire it at Talia, because she's mine. Ooh, that's pretty far, actually.
Impressive.
Now,
Distance.
what if I were to put it in a big long tube like this?
Oh, it goes so far.
How far could it go?
Way farther.
Way farther?
Yeah.
Like, could I get it all the way back to Brett?
Maybe.
I don't know.
No, it'll go, I think it'll go farther.
There's more friction.
Yeah.
There is a little more friction, that's true.
Maybe it's like a
But
sand
by the
sort
time
of.
you get to the end, it's not gonna be good, the force will be blowing it.
You think so? Okay.
It'll be condensed more.
Now I'm
It'll go now.
gonna. Would you agree that I blew about as hard as I could there?
Yeah.
About 90% probably. I didn't go all out because I didn't want to hurt Todd. Now Brett, on the other hand, you don't think so?
I'm saying fuck.
Holy
Holy,
Do it
I
again.
was not expecting it. Ow.
Yeah, eh? That's the reaction I always get. It's awesome.
recycling?
Yeah.
That's farther than I thought it'd go. Wi-Fi router comes out.
Holy crap, that's insane.
So that's the whole idea behind a blow dart. Now, if only I had a second tube
He has a second tube.
I can connect it to. Can we go in the hallway? Of course we can. Can we go there?
This guy is full of them.
Brett, you bring that, okay? I'm not sure why I put it together first. Can you guys put that back up?
He just showed us.
Oh, I just wanted to say, I just wanted to come back. There you go.
It was recorded.
Oh, was it? Oh.
That was the coolest thing ever.
That big fire explosion was awesome.
You know,
Now, I did tell you, I had a short little copper tube, and it would actually work pretty well. Like, I could go from here to probably EJ with that short little copper tube. People were impressed with that. And then when I realized I could do it with that, it's like, pretty good. Yes. Okay.
The first time you tried that, did you think you would go farther, or did you just want to stick over there?
I actually made the kid put on safety glasses and put a book in front of him when he was catching because I didn't want him to get hurt. I didn't know how fast it was going to come out of there. Okay, shall we do some sample questions? Not near as much fun, I'm sorry.
Oh, you gave us these
I
yesterday?
gave you these yesterday.
You just throw questions at us after that.
Sorry, not near as much fun. Actually, that tube is not actually designed for that.
No.
If I have time this period, I will show you what it's actually for, because I never get to that point in the curriculum. Or maybe we should have left it down. Okay, easy questions. What force will give a 1 kilogram mass at velocity of 4 meters per second in 3 seconds? So we have a mass, we have a velocity. Actually, we have a change in velocity, right? Because it's going, it doesn't say it, but it's going from 0 to 4. And we have a time, right? So, oh, hey, this is a fat math question. Now, obviously it is because that's today's topic. But you're going to have to recognize that that is on your own. I will warn you, there's not a whole lot of fat math questions on the test, like maybe 1 or 2, because they're pretty straightforward. Well, it's just like, I do one, okay, they can do it, right? Like, it's pretty simple. So, we are solving for force here, so that's true. The time is 3, so F times 3 is equal to my mass. Johnny, you should have got these questions yesterday. And the delta V is 4. So F is going to be 1 times 4 all over 3, which would be 1.3 newtons. That's how simple these are. Would you expect that to be a multiple choice question?
Yeah.
Yeah, probably.
No.
Okay, good? Question number 2. Says a 10 Newton force acts on a 2 kilogram mass for 5 seconds. Find the impulse, find the change in momentum, find the final velocity of the object. You guys should have this question, right? And they went, oh, Marley's away. That's who's away. You'll have to tell her how awesome that demonstration was. Okay, so we've got the force, we've got the mass, we've got the time. Now, impulse, remember, was the left-hand side, right? So that's going to be J equals F delta T. Carter, why didn't you just stay there at the start? J equals F delta T. Yeah, it's just 50, right. It's 10 times 5. Oh, now, the big question is, what is the unit? Well, we combine the units that we're multiplying. So force is measured in newtons, and time is measured in seconds. So the unit for impulse is not some name, some famous scientist, not a McQueen or anything. It's just Newton seconds. It's not newtons per second, Newton's times seconds. Newton seconds.
Can we just put
NS. You quite often see it with the dot, but it's not meant for
So I can just do NS?
NS, yeah. Newton
Why don't we
seconds.
come up with a unit?
I don't know. And a good question is like, what?
Do you call a Newton a second?
Well, no, but what defines or what kind of units are required to name it after someone, like a joule, or I haven't talked about joules yet, but like newtons or joules or coulombs of charge, or like there's some that have a person's name attached to them, right?
For people who just get it.
Say again?
If you say per, sounds cool. If you just say Newton second.
It seems weird. Well, that's just because you guys aren't used to it.
Yeah, what is it?
well, is it the same thing as newtons per second?
No, because that would be newtons divided by seconds. This is newtons times seconds. That'd be like saying force multiplied by time is the same as force divided by time. It's force times, exactly. Okay, so now what about delta P? How do I get that? Because delta P is equal to m delta V, but I don't got the delta V. But remember that J, like it's fat equals that. So really it's like J equals delta P, right?
That's the whole.
Like the J is the left-hand side,
And then
and then the delta P is simply the right-hand side, right?
You could just go 50 equals.
You could go 50 equals, yeah. In fact, delta P equals 50,
What?
right? Because the J is equal to the fat mab, which is equal to the M delta V, which is equal to delta P.
Okay, but you have a mass.
No, J equals F times T, which equals M times V, which equals delta P. All four things are equal.
So all of them are equal.
All of them are equal, Cassie.
Instead of equal.
Yep. The mass times the velocity is also going to be 50.
So if you have the time and the force, you'll find the momentum.
Right. Now, here's the next question. Isn't the unit for momentum something different than Newton seconds?
Yes.
Right? So it's kilogram meters per second. Right? Kilogram times meters per second. So oddly enough, and you might want to write this in a different color or differentiate it somehow because we're talking units here, a Newton second is equal to a kilogram meter per second.
Yeah, that makes sense.
You're right, because what is a Newton?
It's
Mass times.
Yeah, which is mass times acceleration, right? So that's a kilogram meter per second squared.
Yeah.
I don't want to read that.
I'm not going to do into the formulas, but just be aware that Newton seconds and kilogram meters per second are equivalent units. Okay? You should be aware that those units are equivalent. Yeah, but really you only should use Newton seconds when you're talking about impulse, and you really should use kilogram meters per second when you're talking about momentum. They are equal, but they're kind of used at different times. Kind of like in French. Anybody French? Any French immersion people in here? Okay, so like vous and tu, right? They mean the same thing. They mean you, but you use them at different times. Or tu and usted in Espanol. It means you. If I was speaking to you, like for example, in Spanish, they just have different languages. It's okay. In Spanish, I would refer to you as tú because, how do I put this? I'm the elder here, and so I speak down to you. That's just the way the language works, right? But if you're speaking to me, you would call me like Mr. Bennett. You would say usted when you're saying you. If you said, Mr. Bennett, do you have my text? You would say, usted tengo getting me.
Test you.
But if I'm talking to you, I would say.
Good answer.
How did we get talking about that? Equivalent, just use it different times. Okay. How is this the last one?
We didn't do
Oh, we didn't do C. Oh, the final velocity. Okay. So C, the final velocity. So let's write delta P is equal to M delta V, right? So the change in velocity is 50. What's the mass? 2. So that means that the change in velocity would be 50 divided by 2. So after it's going up, it would be 25 meters per second.
And that's the change of velocity.
That's the change in velocity.
Is asking for the
Well, I guess because the initial 0, therefore final is 25 too. Right?
So we can.
Do you want to try one? Try that one on your own. Ready? pretty straightforward, really, right? Once you sort of talk your wits all through it. How much time will it take to slow a 5 kilogram body moving at 20 meters per second to 5 meters per second if a braking force of 10 newtons is applied? Okay, so I guess because we have two velocities, the first thing is to find the change, right? So VF minus VI. The final is 5. The initial was 20. So we dropped 15 meters per second.
Are you gonna want us to show this step?
You can, I mean, with simple numbers like that, you probably don't need to, right?
I thought you were just gonna say the multiple choice question.
This might still be multiple choice. This is a two-step question, but it's certainly simple enough that you can do multiple choice, right? Yeah. Yeah. And again, reminder, just because the answer that you got is there doesn't necessarily mean it's right. Right? I know what mistakes people make. Right? Like they might have 25 for meters per second. F delta T equals outlandish. You don't hear that word too much. 10, we're solving for time. The mass is 5, so that's going to be, oh, now what happens here? Yeah, but that's going to be, I heard you guys talking about negatives here. So 5 times, so that would be 5. So you just make it positive?
Yeah.
There's a mathematical reason.
You multiply by what? Negative one.
No, but just because? So that time is positive? It's
Well, it's slowing down, so.
it's slowing down. It's a braking force, right? And so the force is in the same direction as the, or it's opposite to the motion, right? So it's really a force of minus 10,
Oh, I thought about that, but.
right? I'm glad you realize, oh, time can't be negative, but that's the reason why, right? So that's going to be 5 times 15 is 75, so I think it's 7.5, right?
You were gonna make the triangle correctly done for me.
Say again?
You didn't include the
You're right, I didn't.
Does it matter?
Not really. I mean, generally the initial time is 0, right? Because the question is how much time. It's very rarely at what time does it,
Yes.
right? It's usually how much time has elapsed. So the initial time is 0. Yeah, I just tend to sort of forget. Okay, now briefly here, how does all this apply to a car in a crash? This was explained yesterday.
Oh, yeah.
How does this apply to a car crash, Sarah? Do you remember? What did they show at the front of the car? They showed that the steel was like a different color, right?
Yeah.
And what was happening at the front?
Is there enough weight to hold up the
It
engine?
crumples, right? So the front of the car crumples. The what do they call it? The compartment, the passenger compartment, is very rigid, right? Very solid. But the front of the car is supposed to crumple. Now, why is it supposed to
Slow
crumple?
down, slow down, extend the time.
Extend the
Yeah.
time. That's the answer I'm looking for. It extends the time, and so, Johnny, F delta T is equal to M delta V. So, is the mass of the car staying the same? Oh, I need that in a different color. Rats. Is that going to be different things? Yes, okay. Delta T equal to... Does the mass of the car stay the same? Does the change in velocity of the car stay the same? Like if it's got to go from 100 kilometers an hour to stop, the change in velocity is the same, right? So I can't change in a car crash. I can't change what's on the right-hand side. But I can extend the time, and to keep the whole equation balanced, if I make the time so much bigger, then that does what to the force? Makes it smaller, which means you are more likely to survive the crash. Okay, so in fact, it is the exact opposite of following through, right? You are following through the crash. If Ty throws me the ball, and I just put my hands up like this, well, it just bounces off, right? And if I'm playing baseball or you're playing football and it's really thrown at me, right, and I do this, what am I doing when I do that? I'm increasing the amount of time, which decreases the force, which means I'm more likely to hang on the ball. That's why when you're fielding the ground, you're supposed to do
Well, you
that.
could have taught us that when the season was still.
Turned out okay.
Yeah, well,
Did you really think you want a physics lesson out there why you do that?
yes.
Really?
Sweet.
It is pretty straightforward. But they do teach you that. When you first play baseball, they teach you, right, to do this and bring it in like this, right? And that's what you're doing, is you're decreasing the force by increasing
Could you imagine how unreal Ty's ratio would be though?
the power of physics involved in the football, right? I'd be like a consultant.
100%.
I'll wager a guess that most baseball, most football coaches don't understand the physics involved. They just know that you do that, right? They slow it down. You're basically slowing it down slow. Can you think of any other examples where that kind of thing applies?
Trying to catch an egg.
Trying to catch an egg?
Or maybe like,
Water balloons,
you
right?
know, when a goalie catches a puck.
Yeah. Anytime you're trying to slow something down, you want to do that. Even if you if you're jumping off a ledge or something, right? You jump down, what do? You bend your knees, right? So you're increasing the amount of time.
I think I was just
Versus what?
before you like the bend.
Well, but the reason you don't get hurt is because the force is
That's why people roll.
small.
All the force just goes through them.
We should
Sorry.
see how high we could jump from without breaking our legs if we bend.
You do that on your own time.
Tell us how to. Alright.